What up, Calculus students? Mr. Messer coming at you. This year, I am going to attempt to do the lesson videos in person versus in the past. My lesson videos were created just from live classes that I taught, which means they gave a lot of space for practice problems, maybe were longer than what they could be. So I'm going to try to do more succinct lesson videos where you guys can pause if you need to, but you still get the introduction to the concept the way that I want you to get, which is very important for this class. So we'll see how that goes. We are reviewing trigonometry. The key with trigonometry for calculus is to know that it's going to show up randomly. And since it's going to show up randomly, we can't just have it like memorized, ready to like splurt out. We need to just be able to pick it out of our brain here or there. Boom. Oh, quiz 2.3 has got a trig question. I don't want you to have to create the entire unit circle to be able to answer that one trig question. So we're going to go back to how you were introduced trigonometry. I'm going to reteach it to you. And some of you are already there, and this will be like a little repetitive. That's okay. It's an easy start. Some of you, it's going to be necessary for you to really understand that the unit circle is just stuff that you've learned before. And we are going to start in on like making sure we understand things. That's the name of the game. That's how I teach. So you understand versus memorize. All right, so connecting the fact that trigonometry in the unit circle is just like the stuff you've already learned. You learned in geometry that the sine of an angle equals a ratio of an opposite over a hypotenuse in a right triangle. So SOHCAHTOA is used for right triangles. Right triangles are beautiful, beautiful objects because of the Pythagorean theorem and because of these consistent ratios if you know an angle. The cosine of an angle is equal to the ratio of the adjacent side over the hypotenuse that exists in the triangle that has that angle, a right triangle that has that angle. And then the tangent of an angle in a right triangle that has the angle will equal this ratio. So it's just ways for us to be like, oh, here's a right triangle, here's the angle. Oh, here are the ratios you're supposed to see in that triangle, no matter how big the triangle is. Cool. We also know that the reciprocals of sine are cosecant. The reciprocals of cosine are secant. Just like flip the thing. Like flip the ratio, flip the letter. That's what I was trying to say. And then tangent, cotangent. Cool. That's the first thing. You learn that in geometry. What else did you learn in geometry? You learn about like some special right triangles. If we start with an equilateral triangle and then split it in half, let's say the lengths are 2. If I split it in half, we'd get this length 1. And then if I use the Pythagorean theorem, I'd find this length is root 3. Cool. Let's divide all of these side lengths by 2. And we have what's called a unit triangle, or a triangle with a hypotenuse of 1. And this, starting with a equilateral triangle, this would be a 60-degree angle. Split that equilateral triangle in half. This is a 30-degree angle. So we get this 30, 60, 90 triangle with these side lengths. And it's like every 30, 60, 90 triangle has to have the ratios that are the same as these side lengths. So it's like this is the understanding is like you scale this, you get another 30, 60, 90 triangle. Cool. Well, we understand that we could shift the orientation of that and put the 30-degree angle down here, and you'd have this side length, you'd have this side length, and this is still 1. And then if we talk about a isosceles right triangle with a 45-degree angle, we can use the Pythagorean theorem if we wanted to find like these lengths. We'd have 2a squared equals 1. We'd get a squared equals a half. We square root, we get a equals the square root of a half, which simplifies to be the square root of 2 over 2. Okay, so these are like special right triangles, and you probably remembered from geometry the 45, 45, 1, 1, root 2. We'll divide everything by root 2, and you get that. Great. If you remember these triangles from geometry, you actually know the unit circle, and you're done. With one certain exception is that we don't use degrees, we use radians. And radians are important because degrees are very much an earthly number. Degrees, 360 degrees, used for a circle because there's about 360 days in a year, and 360 is a good number that can split into things evenly. This is very much of the earth. 2 pi is universal because 2 pi is the circumference around a circle, radius of 1. Cool? Now, whenever we refer to 360 degrees, it's like, well, what's 0 degrees? Where do we start? Well, it's important to know that when we're looking at a XY axis and we decide to talk about angle measurements on an XY axis, so this is like the Y axis, this is the X axis, that the X axis looking off to the right is where we start. So like imagine you are a person, you are looking off into the distance and you're looking at the horizon, maybe your 2 hands are together, that is an angle of 0. Okay. And then as we start looking up, we are looking positively. If we look down, we look negatively. We're going to say that if you start going around counterclockwise, you'll be adding angles. If you go clockwise, you will be subtracting angles. Cool. And if we go all the way around the circle in this counterclockwise direction, we will end up at 360 degrees back where we started, or at 2 pi radians. Great. Well, what if we went halfway around the circle? We'll divide this by 2 and we get 180 degrees. Boom, pi, 180 degrees. Great. Now there are some other special angles that we are going to talk about. Once my cursor comes back, we'll talk about them. Sometimes my cursor disappears on me and I can't do anything about it. I wonder what happened. Here, we're back. For example, let's divide both of these by 2. Well, 180 divided by 2 is 90. Pi divided by 2 is pi divided by 2. All right, so 90 degrees, quarter way of the circle is pi over 2. Let's take this and divide it by 3. 180 divided by 3, 60. Pi divided by 3 is pi divided by 3. All right, well, 60 degrees is pi over 3. So if I go up, what we are familiar with as 60 degrees, we say that is equivalent to pi over 3 radians. And let's take 180 and divide it by 6. 180 divided by 6 is 30. 30 divided by 6, pi divided by 6 is pi over 6. So if I go up less, if I go up 30 degrees, we get pi over 6. And what I realize, and I'm going to come back up here, is that, the tall 30, 60, 90 triangle, I'll say this later, actually. I'm going to save that for later. That'll be next. We'll get there. Okay, cool. Cool. Now, what about these other angles? Well, what's easy to do is understand adding versus subtracting angles. So, let's say we are at pi, 180 degrees. Let's add and subtract 30 degrees from pi. So, if I take 180 and subtract 30, you're like, oh, that's 150, no big deal. But the question is, what is pi minus the pi over 6? Well, this is what we like to understand, and especially with radians, it's easy to work with radians. You don't have to do that many calculations, provided you know how to subtract these two things. What is pi minus pi over 6? Well, I like to write this as 6 pi over 6 to give it a common denominator. And 6 pi over 6 minus 1 pi over 6 is 5 pi over 6. So all of a sudden we realize that if I subtracted 30 degrees, I get this radian measurement of 5 pi over 6. Well, if I took 6 pi over 6 and added pi over 6, I'll get 7 pi over 6. 6 pi over 6 plus a pi over 6 is going to be adding 30 degrees, and I get 7 pi over 6. Great, I could do the same thing with 60 degrees. What happens if I subtract 60 degrees or add 60 degrees from pi? Well, you could do it with 180 plus 60 or 180 minus 60, but it's actually not that bad to do pi plus 60 degrees or pi over 3, or pi minus pi over 3. I like to write this as 3 pi over 3, and I get 4 pi over 3. Now make sure we understand 3 pi over 3 plus goes in this direction, we get 4 pi over 3. 3 pi over 3 minus a pi over 3, we get 2 pi over 3. Cool? What about some angles over here? Well, I'm going to go all the way around to 2 pi and subtract 30 degrees and subtract 60 degrees. And I'm going to kind of do the same process, only I have to go all the way around to 2 pi, and I'm going to take 2 pi, and I'm going to subtract pi over 6. I'm going to take 2 pi, and I'm going to subtract pi over 3. Well, 2 pi is 12 pi over 6's, or 2 pi is 6 pi's over 3. All of a sudden, I get 11 pi over 6, and I get 5 pi over 3. And that's like an easy way to be like, okay, this is a pi over 6 because it's got a 30-degree angle. It's 30 degrees away from the x-axis, and this pi over 3. Cool. We could do the same thing with the pi over 4's. Challenge for you guys is to try to figure out the pi over 4 measurements that are in all the quadrants, not really worrying about degrees, but by working with adding and subtracting from 0, from pi, and from 2 pi. So go ahead and try that, and you should be able to get these angles, that this is pi over 4. This will be 4 pi over 4. Subtract a pi over 4 is 3 pi over 4. This is 5 pi over 4. This will be 8 pi over 4 minus a pi over 4, which is 7 pi over 4. And then we forgot about this one, which will be adding a pi over 2 to pi, or subtracting, and 3 pi over 2. All right, it's very important to realize that pi's over 3, always 60 degrees away. Always 60 degrees away. 60 degrees away from the x-axis. Pi's over 6. Pi's over 6. Always 30 degrees away from the x-axis. And this might be repetitive. You might already know this, but I'm just making sure we have it down and it's mastered before we move on. Cool. So if I ask you to find where is 7 pi over 6, if I ask you to find where is 5 pi over 3, you should be able to work it out by understanding that it is a pi over 6, or it is a pi over 3 away from an important angle. This, I would say, is 6 pi over 6 plus a pi over 6. This, I would say, is 6 pi over 3 minus a pi over 3. You could do 3 pi over 3 plus 2 pi over 3, but it's not as easily done as 6 pi over 3 minus a pi over 3. So where are we? 6 pi over 6 plus a pi over 6, boom. I'm right here. I've created a 30-degree angle with the x-axis. I am in the third quadrant. 6 pi over 3 minus a pi over 3, 5 pi over 3. I'm right here. I'm creating a 60-degree angle with the x-axis. If I ask you where is 3 pi over 4, well, I would have done 4 pi over 4, or pi, minus a pi over 4. Go right there. Okay, here's pi, subtract, add. Don't forget that. Great. Then what we realize, why is it called the unit circle? It's called the unit circle because it's a circle with a radius of 1. Radius of 1, radius of 1. And what we realize is that we can use our triangles that we already know, and our triangles can go inside this circle because the radian measurements of pi over 3 creates the tall 30, 60, 90 triangle. The radian measurements of pi over 6 creates the short 30, 60, 90 triangle. And the radian measurements of pi over 4 create the 45, 45, 90. So if I ask you, hey, what's going on at pi over 4? Well, you'd be like, well, that's just 45 degrees. And I actually create a triangle that I know, the 45, 45, 90 triangle. And now you see the triangle. And now if I ask you, what is the sine of pi over 4? You should be like, well, SOHCAHTOA, opposite over hypotenuse. The hypotenuse is always 1. I don't have to worry about it. There's my answer. Let's look at this angle, which is 5 pi over 6. It's 1 pi over 6 less than 6 pi over 6. Pi over 6 is always create a 30-degree angle. We always then see the triangle that's created. We have a root 3 over 2, and we have a 1/2. Root 3 over 2 bigger than 1/2. Probably should have said earlier, you should understand that root 3 is bigger than 1, and root 3 over 2 therefore is bigger than 1/2. The one thing we have to be careful of is that this is the y-axis and this is the x-axis, which means if we're in the second quadrant, we are actually moving left on the x-axis if this is the origin. And we're moving up on the y-axis. So then if I ask you, hey, what is the cosine of 5 pi over 6? You could say, oh, SOHCAHTOA, adjacent over hypotenuse. Oh, negative root 3 over 2. If we go to this angle, which is 5 pi over 3, we would go from 6 pi over 3, subtract a pi over 3, and realize that it's a 60-degree angle. It's a pi over 3. And we realize that we have the side lengths. Sorry for being messy here, but I am messy. Side lengths of a half and side lengths of root 3 over 2. Only difference is I'm going down on the y-axis, so that's why it's a negative root 3 over 2. So if I ask you what is the tangent of 5 pi over 3, you could actually just think about the triangle, and you could use SOHCAHTOA. It's not anything new. It's stuff you already know. Well, one difference being like these negative side lengths. That, I guess, is new to pre-calculus, is negative side lengths. But you could have been asked what is the tangent of 60 degrees in your geometry class, and you should have been able to get it using SOHCAHTOA. Opposite over adjacent. Now, one thing we notice is that the angle we are always referencing is always the angle created with the x-axis. That is something that is just also something that needs to be known, is that we're not creating a triangle with the y-axis and talking about this angle. We are creating it with the x-axis. Well, if the hypotenuse is always 1, what we realize is like the sine of our angle is just going to be the opposite side divided by 1. Well, if you divide by 1, nothing happens. Well, if the angle that we're referring to is always this reference angle with the x-axis, the opposite side is always this vertical length. Vertical length, vertical length. Well, if we're on an xy axis and we have this vertical length, we always refer to that as our y coordinate, or our y length from the x-axis. I actually don't go here. I stay here. And if I'm asked what is the sine of 2 pi over 3, Coordinates don't go in my brain, but the triangle that is a 60-degree triangle goes into my brain. And the lengths of that triangle goes in my brain. I find it's easier in my brain to keep those triangles, those special triangles in there and not make something else have to be in my brain to memorize this unit circle. So I don't go to the coordinates, and some of you might want to try not going to the coordinates. You might want to try just going with lengths of triangles, and that you use a lot in like high school mathematics, these special right triangles. What we realize if we take the cosine of an angle, the cosine of the angle is the adjacent over the hypotenuse. Well, since the hypotenuse is always one, and it's always a positive one, that the cosine of an angle in the unit circle is always going to be the adjacent. Well, the adjacent is always going to be this horizontal length, whether it's here or here or here. Well, if you were to look on a point on the unit circle, yes, this horizontal length would be this x coordinate. So you could go to the x coordinate, but I like to just kind of stay here, like the horizontal length. This is the vertical length, this is the horizontal length. And then tangent, nothing special, opposite over adjacent. Well, opposite is always the vertical. Adjacent's always the horizontal. And we could just like stop there instead of having like, oh, tangent's y over x or tangent's this or this, okay? So that's what I do. If I'm asked what's the sine of 2 pi over 3, I don't think about coordinates. I think about triangles. I say 2 pi over 3 is here. It's 1 pi over 3 away. It creates that 60-degree tall triangle. I understand that I'm going to the left. I'm going up. Sine opposite root 3 over 2. I mean, I usually use my hands, like cosine of 7 pi over 6. I go to 6 pi over 6. I add a pi over 6. This might be opposite for you guys. I know I'm going left and down. I know that it's a short 30, 60, 90 degree triangle. It's the 30 degree, which means it's a longer horizontal and a shorter vertical. So if I have 7 pi over 6, the horizontal is negative root 3 over 2. Now, if you want me to show that, I would probably go 6 pi over 6, add a pi over 6. Here we go. 30-degree angle. 30, 60, 90 special right triangle. Keep track of moving left and right. Hypotenuse is always 1. You don't even have to worry about the hypotenuse because it's 1. Cosine. If you're asking for the secant of 5 pi over 3, it's nothing special besides find the cosine of 5 pi over 3, get your answer, and flip it. Okay, pi over 3's 60-degree angles. The cosine, always the shorter side. The cosine is always the adjacent. It's always the horizontal. So 5 pi over 3 is going to be a 60-degree angle. It's 1 pi over 3 away from 6 pi over 3. Here's 5 pi over 3. We have the adjacent. We have the opposite. The adjacent is 1/2. The secant is the reciprocal of that. Cosecant of 5 pi over 6, I'm going to find the sine of 5 pi over 6. And I'm going to go to 6 pi over 6. I'm going to subtract a pi over 6, and it's 5 pi over 6. And I'm going to see that it's going to be, oh, why did I do this? I should have said 5 pi over 3 as well. So I'm going to change that for the notes. Let's go 4 pi over 3. These are my notes. I can do whatever I want. So 4 pi over 3, we have an adjacent, which is negative 1/2, an opposite of negative root 3 over 2. The sine is going to be negative root 3 over 2 because it's the opposite. It's the y distance. It's the y coordinate. It's just a tall 30, 60, 90 triangle. You could literally start with this. You can really say, okay, root 3 over 2, 1/2, 1. Root 3 over 2 is bigger than 1 over 2. Great. Sine flipped. Okay, flipping. We get that. We'll talk a lot about in this class. Free response, you do not have to simplify. So this is acceptable for free response. However, for multiple choice, lots of answer choices will be simplified. So you will be asked to potentially simplify, potentially rationalize your answers for so that you can get the multiple choice selection that is the correct selection. All right. A couple more I'm going to do in my head. 12 pi over 6, 11 pi over 6. That is a short 30, 60, 90 triangle. It is in the fourth quadrant. So it's got the longer adjacent, the shorter opposite, tangents opposite over opposite over adjacent. And we will get negative 1/2 times 2 over root 3, which is negative 1 over root 3. If we multiply straight across and then simplify, and then we can rationalize that by multiplying the top and bottom by root 3. And if that's confusing to you, great. Sine of 5 pi over 4, negative root 2 over 2, because this is our first 45, 45. Pi's over 4, 45 degrees, 45 degrees. Root 2 over 2. Cool. Sine, opposite. 5 pi over 4, 1 pi over 4 more than 4 pi over 4. Cool. Knowing that the cosine of an angle is always equal to the adjacent over the hypotenuse, with the hypotenuse being 1, which is the horizontal, we realize we can just look at the x distance, or the x displacement. The sine, vertical, opposite, vertical. Tangent, vertical over horizontal, or y over x. When we get to an extreme, or what's like a quadrantial angle, we realize that we can't see a triangle. Now I'm going to let you know a triangle is there. Say we're talking about 0 degrees. Here's 0 degrees. Here's 0 degrees. I don't see a triangle, Mr. Messenger. Well, I'm going to tell you that there is a triangle. Here's a triangle, and I'm being very exaggerated because it doesn't look like this, but I'm going to show you what the lengths are. The hypotenuse is always 1, always positive 1. But over here, I'm going to say I don't have any vertical length. I do have a horizontal length. So just imagine the hypotenuse and the horizontal being smashed on top of each other and the vertical not existing. It's still a triangle, just two sides are length 1 and one side's length 0. Confusing? Maybe. If it's confusing, don't do it this way. Just think to yourself that cosine is always like the horizontal displacement, always the x length, and you could be like, well, this x length is 1. So that's why this is 1. You know, you're going to the right one, but you're not going up or down at all. So that's a possibility. Let's say pi over 2. Well, Mr. Messer, I don't see a triangle at pi over 2 either. It's like, I kind of do. I want you to see it might not be something that you like to see, but the hypotenuse is always 1. And I'm just going to say the vertical length is 1, but the horizontal length is 0. So you could see the triangle, you could see the cosine, you could see the sine, you could see the tangent. And maybe that's something you can do, or you can go back to cosine's always the horizontal here is 0. Sine is always vertical. The vertical of this first one is 0, but the vertical of this second one is 1. I'm going up 1. That's my y displacement. I'm going left and right, 0. Cosine of pi, -1. The sine of pi, 3 pi over 2, -1. Why? Because at pi, I'm going to the left 1. I'm not going up or down at all. At 3 pi over 2, I'm going down 1. I'm not going to the left or right at all. Cool. Then we move on to solving trig equations and different types of questions. Again, this is review, and I am going fast. We're going to need I feel like we're going to need the entire lesson for this if I want to do it my way. We got a trig function of an angle equals a ratio. That's trigonometry. Trig function of an angle equals a ratio. Well, just earlier, we asked what is the cosine of 0? 0 refers to the angle. And we want to know the ratio. Well, angle of 0 adjacent over hypotenuse, 0 over 1, 0. Versus the cosine of an angle equals a ratio. Oh, this is the ratio that I'm given. We are wondering, what is the angle? So this question refers to what are the angles. Here, cosine of 0, 0. Here, when is my ratio equal to 0? When is my adjacent over my hypotenuse equal to 0? What are the angles that creates that? It becomes a backwards kind of situation where I'm kind of given the answer. I'm trying to find the question. Well, the answer to this question would be pi over 2 and 3 pi over 2 if we're talking about angles between 0 and 2 pi and not going outside of 360 degrees. Why? Many ways to think about it. The adjacent, the horizontal length being 0, where does that occur? Up and down. What I like to do when it's not at the quadrantial angles, when it's like sine of x equaling negative 1/2, is start with the trig function. It's like, okay, sine is the opposite over the hypotenuse. So I don't have to worry about the hypotenuse because it's 1. The opposite is the vertical being a half. And I think about my triangle where the opposite is a half. And I think about my 30-degree triangle that occurs at pi over 6. I say that opposite is a half. Cool. Hypotenuse is 1, adjacent root 3 over 2. Well, then I think about the sine. Sine of an angle equals negative 1/2. Well, if I am trying to find out when sine is negative, this is some mnemonic that might be able to help you. It's called All Students Take Calculus. And it just helps you remember what trig functions are positive where. Here, all of your trig functions are positive in the first quadrant. Here, sine is positive, and only sine and cosecant are positive. Here, this represents tangent being positive in the third quadrant, and cosine. And you should understand why only sine is, say, positive in the second quadrant. We're going up in that second quadrant, but we're going left in that second quadrant. We have negative x's and positive y's. This is why sine's always positive, because sine's always the y or the vertical distance. So here's what I do. I say, okay, I want the pi over 6's, and I want the pi over 6's here and here in the third and fourth quadrants. I need to find those angles, and those angles, I'm going to be very exaggerated with this, are always going to be a pi over 6 away from things. So I need to be a pi over 6 away from pi and 2 pi. I do 6 pi over 6 plus a pi over 6, I get 7 pi over 6. I do 12 pi over 6 minus a pi over 6, and I get 11 pi over 6. Cool. Sometimes we're going to ask you to find all solutions. Sometimes we'll ask you to just find the solutions between 0 and 2 pi. Say I ask you what are the angles in which the cosine of the angle equals root 3 over 2. Well, cosine is the adjacent. The adjacent is always the horizontal. Here's my horizontal. Here's going to be, okay, my pi over 6. My pi over 6, where cosine is positive, all students take calculus, is this pi over 6 and this pi over 6. So this is going to be 1 pi over 6 and, okay, 12 pi over 6 minus pi over 6, 11 pi over 6. Now, if you remember, we could also have another angle if you go around the circle and end up in the same spot. It's called a coterminal angle. These are not the same angles, but they have similar properties. They end up in the same location. They will have the same ratios, but they're different angles. It's like What's the difference between a 360 and a 0? Well, one of them you spun around, and the other one you just didn't do anything. We could go around our circle by adding or subtracting 360 degrees or 2 pi. If I said what could be all of the solutions, not saying between 0 and 2 pi, I could say, well, these two angles and all of the coterminal angles. We like to say plus 2 pi k, where k represents any integer. Negative integers, 0. So we say like k belongs to the integers. This is kes, as you heard from your pre-calculus teachers. And all of a sudden we just turned some solutions. These are the solutions from 0 to 2 pi. And just by adding this, you get infinite amount of solutions. All the solutions. So for sine x equals negative root 2 over 2, I would say we have 5 pi over 4 and 7 pi over 4. These are the solutions from 0 to 2 pi. And then if I add 2 pi k, where k belongs to the integers, we would have all of our possible solutions. Cool. If you're ever dealing with tangent or reciprocals, sometimes tangent is tricky. Well, just figure out which triangle is going to work. It's either going to be the pi over 6 or the pi over 3. You know it's not going to be the pi over 4 because you should think about what happens at pi over 4 with tangent. Opposite over adjacent, and then the correct quadrants. But maybe you need to do a little bit of work of which one, when we do the opposite over the adjacent, gives us this root 3 over 3. If you haven't done it yet, try it. Try an opposite over adjacent for this one, try an opposite over adjacent for this one, and see which one wins. And the answer is this one. It's because 1/2 divided by root 3 over 2 ends up being 1 over 2 times 2 over root 3, which is 1 over root 3, which turns into root 3 over 3. So we want the pi over 6 where tangent is negative. Tangent is negative in the second and the fourth quadrant, so I want this pi over 6 and that pi over 6. So those pi over 6s are 5 pi over 6, which is 1 pi over 6 less than 6 pi over 6, and 11 pi over 6. Cosine negative 1/2 is what I would do here. If I have a reciprocal, if I ask you when is secant of x equal to negative 2, my question would be when is cosine equal to negative 1/2? And now I'm going to think about, okay, the pi over 3 triangle has the adjacent of 1/2. So I want the pi over 3's. Where's cosine negative? Cosine is negative here and here. So I want the pi over 3 here and the pi over 3 here. This is 3 pi over 3. Subtract, add. 2 pi over 3 and 4 pi over 3. Cool. Great. When is the horizontal length 0? Pi over 2, 3 pi over 2. When is the vertical length 0? 0, pi, 2 pi. Remember, like here, it's just to the right. Here is just to the left. It's not up or down at all. Here, we're just up. Here, we're just down. If you want to go to the points, that's fine. I don't like doing that, but of course you can. When are we going down? 1, 3 pi over 2. When is the opposite over the adjacent undefined? Well, it's important to remember a number divided by 0 is undefined. 0 divided by a number is 0. How do I remember this? I always like to do 8 divided by 2 is 4. Why do I like to do this? Because it's like 2 times 4 is 8. Okay. If I said it was the other way around, does that make sense? 0 times 0 is a number. No, that's not true. 0 times anything is 0. So, versus here, a number times 0 is 0. I'm not sure if you can see this because of my face. So, I want a situation where I have a 0 in the denominator. That's the adjacent. That's the x. That's going to be at the pi over 2's. There. Finally, what happens if there's more than just theta or x inside your trig function? Well, just remember it's the trig function of your angles that equals your ratio. Well, here your angles are represented by 2 theta. Those are your angles. Well, what can be your angles? Well, 2 theta, my angles 2 theta, can be, okay, 1 sine root 3 over 2. I need my tall 30, 60, 90 triangle, pi over 3's. I need my pi over 3's in the first and the second quadrant. And I get 1 pi over 3 and I get 2 pi over 3. And I want all solutions, so I want these plus all of their coterminal angles. I'm going to then have my angles. But what are my solutions? My solutions are what theta are. So I'm going to solve for theta by multiplying by 1/2. I don't think this is going wrong. This might be too much on day one. Well, we'll see. I think the way that I'm teaching this is not like slow enough. I'm trying to get through all these examples. But... well, it's giving me good perspective. I'm able to like maybe say, ready, set, go. I don't know. Here, my angles are x over 2. We want 5 pi over 6 and 7 pi over 6, and we want multiples of 2 pi for that. I go slower for the other lessons. Long lessons. This is a lot. I think it'll be fine. We'll see how long this video ends up being. And I'll get 5 pi over 3, 7 pi over 3, and multiples of 6 pi added to that when I'm solving for my solutions. So, angles to solutions. I explained that in the homework video a little bit better. What happens if you have sine equaling cosine? Well, a lot of people mess up and they just say the answer is pi over 4. But just be careful. Sometimes you can do something so you can see, oh, it's when is tangent equal to 1. Tangent's equal to 1 at the pi over 4's, but it's the pi over 4 where tangent is positive. So that would be that with all of the solutions. All right. It's a lot. And if you don't understand it, sometimes going to memory is always like a good fallback. But one of my students wrote me a letter over the summer and said, like, memorization doesn't travel. Memorization you can't take with you. It's tough to take with you. Understanding can travel. Understanding will help you in the future when we have trigonometry and right triangles and trig functions and the Pythagorean theorem. Understanding of that, of the unit circle this way, helps you with those things in the future. Trying to not make more, but to understand more with like less. So if you don't understand, I challenge you to try to learn how to understand and not rely on the unit circle. And if you need help, I would love to help you come in for extra practice. All right? Peace.